Yeah, so just divide the regular wavelength by the index of refraction, and you get this modified wavelength, and then put that in the usual formula, and out would come the angle.
Is that effective? I mean, that's okay. Yeah, that's essentially what. Okay, yeah.
Yeah.
Do you have to take into account that they were using 1.00029 for air instead of just 1?
Oh, heavens. Well, if you want to carry a whole lot of digits, then I suppose you should.
They just listed that in the problem, so
I think that's a red herring. I don't see how that's relevant.
Okay.
I mean, if you wanted to get the answer to, what, 6 digits or 7 digits of precision, yeah. But most of you are rather at the other end of that spectrum. If I had anything to criticize, I see a number of you are doing problems with, at best, 2 digits of precision, and you rather quickly lose precision. And so, anyhow, no, I would just ignore that.
Generally speaking, is there an amount of significant digits you would like us to
the general rule is 3 when you're doing stuff. You keep 3 digits of precision. Even in problems, in physics books, we aren't, what should we say, anal about the rules for significant figures. And I think it's in part because the physicists are aware enough of weird things to know that that is a crude rule of thumb, that it can pretty often be wrong. And so we tend to just ignore it. So I'm not sure, Hecht maybe is more consistent about it, but physics textbooks often give you information that has only 1 digit of precision. You know, something is 3 meters long, and well, you know, they don't bother to say 3.00. But just for the sake of getting answers to be able to compare with each other and see, are we doing this the same way or not, the assumption is that you're doing 3 digits of precision.
Okay.
If the other thing to say about that is, if you ever are working in a problem in which you realize you're subtracting 2 numbers that are nearly the same, then by gum, you better keep a lot of extra digits of precision, because you will lose precision in that subtraction. That's one of the most common ways to get messed up. But I don't think we've been doing that here lately. Yeah. Okay, well, that was 8. What was next here? 12? That's what I've got next. Did you get 12? Have troubles with 12 or not?
What?
Hard one? Yeah, you don't know what
you were fairly confident on this one.
Okay, well, here's what I've got.
Yeah, that's what we got.
4.5 millimeters.
Mm-hmm.
Yeah. Yeah, that's a fairly straightforward problem. Okay, and then coming next is 14. So that one, you're trying to prove something. So did you get it or not? Yeah, weren't able to do that.
We did not.
Okay. Well, here's what I've got to start with. So there's 2 effects. You've got the single slit effect that gives you this sort of broad central maximum. And then 2 slits, if they were really narrow slits, would just give you a sort of sine wave oscillating along that has peaks. These go together then to make the usual figure that, you know, would oscillate back and forth and shrink down as it goes. So, you know, something like this. And the question is, how many of these peaks will be contained within that central maximum if you were to count them? So I just find where are the zeros, where are the limits of this central maximum. And using Hecht's sine theta scale for everything. So down here is also sine of theta. So I graph it as a function of sine of theta rather than theta. And these zeros occur at lambda over b. Are you with me so far? He's got this in one of his figures.
B is the width of the slits.
Exactly. He does this somewhere toward the beginning of the chapter, I think. Yeah, 464. That's the figure that I'm essentially copying. And so here's the lambda over b and minus lambda over b. He's got a mistake in here. Somebody did the figure wrong. The minimum here is correctly at pi or lambda over b. Over on the negative side, things got shifted out of line. So this should be lambda over b here. This needs to be there, and that needs to be there. They're out of position. Somebody made a goof. But not me. Okay, so so the range we're talking about is from minus lambda over b up to lambda over b in sine of theta. And then by the same token, you can graph the peaks that are caused by the double slit. And that's just, there's a peak at lambda over a, another one at 2 lambda over a. There's another one at 0. At all values of n times lambda over a. And that, I think, does he have a similar, he has a figure quite like that in here. Seems like he ought to somewhere, but I don't know where it would be. Well, that probably comes from the last chapter. Yeah, here's page 400. Similar kind of a figure. Now, he doesn't have the scale done quite the same. Here it's lambda s over a. I don't even know what s is in this context. But anyhow, that's the same kind of a figure that I'm trying to put together. So we have these peaks happening at lambda over a. Integer multiples of lambda over a. And then the limit up here is lambda over b. So then it's a matter of counting how many, how big can n get? So that, you know, your nth peak is maybe right at lambda over b. So that's what I'm saying here, that n times lambda over a has to be less than or equal to lambda over b for the peak to be within that central maximum. This would be the limit of the central maximum, and this is counting the different peaks within it. From that, I just get that n has to be less than or equal to a over b. That's just rearranging this statement. Canceling the lambdas, I guess. Now from that, if you just say, all right, A is 2B, that's what the problem starts out with, then you can simplify this formula even more by just substituting instead of A, instead of saying that N is less than or equal to A over B, just substitute for that A, M times B. And then the B's cancel. So then you have N is less than or equal to M. N being the index that counts which fringe you're looking at within this pattern. And M being, what is M?
The distance between the slits?
That's A.
Which is what got, it's a, oh no, there's a 2.
I blew it here. I'm confused.
And instead of and, shouldn't you have put 2?
I think so. I think I've got a
And
mistake.
is less than or equal to 2.
Let's see. I'm getting confused about what we were given and what we were trying to find here, because the, okay. Okay, I misstated the problem. All right. It's clear back up here. The statement was that A is equal to M times B. So right here, if A equals M times B, then what I've done here is correct. I made that substitution. Is that making sense now? So M came from the beginning of the problem. So we end up with N being limited to less than or equal to whatever this ratio is, this ratio M between A and B. And then just thinking sort of very concretely about what that means, then the values of N would start at minus M, count their way up to 0, and keep on counting all the way up to positive M. And then if you just count those, you'll have M negative ones and M positive ones and one more being 0. And so that looks like 2M plus 1. The way you get to just 2M is by recognizing that the very end fringes, if this ratio A is M times B, if M really is an integer, then you're going to have one of these peaks sitting right on a 0. And so it kind of gets smashed, and you get a sort of a half a fringe on each side, which is really hard to see. You don't really see those in general unless you can kind of see them in a very few cases. But you have sort of a half a fringe left on the one side, and you'd have another one over here. And we're counting those each as a full fringe. If you count them each as half, then you get 2M down here instead of 2M plus 1. So that's how I got it.
Yeah, he does. It's in the back of the book, but he does a lot of substituting that was pretty hard to follow, with very little explanation of what or where things were coming from.
Yeah, that doesn't surprise me. 10, 14. Oh my. Yeah. Cute. Yeah, well, anyhow, I like my answer better. It takes up a whole lot more space, though, so. Okay, should we move on? That was 14. Now, what am I missing here? Oh, we never did 12. What happened to 12?
We all got the right answer. So
Oh,
we
I see.
skipped
Okay.
over it.
Okay, so we are just on to 17, the last one. Then. Great. Okay. So did you get this one? Were you able to make some beautiful graphs?
We grabbed them, but like we didn't know what else to do.
Yeah. Okay, well, let's look at this in some detail. So we're expecting if we've got, first of all, let's get the relative intensity. What's the relative intensity of the subsidiary maxima? So these little ones, what's their intensity relative to the big ones, presumably, in a 3-slit pattern? And that I just did with these little phasor diagrams. So you can look at the big peak is when all 3 are in line, and a little peak is when you're going back and forth and back. And so this one has an electric field strength of just E0, one factor of E0, the other two having canceled out. And this one is 3E0. So their ratio should be 3 to 1 in amplitude of the electric field. But if you look at the problem, he's asking for irradiance. So you must square that. And so that's where you'd get an intensity ratio of 1/9 instead of 1/3. Okay, then trying to draw the pattern when A equals 2B for 2 and 3 slits. I first did this all sort of by hand and then discovered the joys of Desmos. I have no idea about that. I don't know how long that's been sitting there, but it's a wonderful graphing calculator. So here's what I did. The single slit pattern, I mean, you've got essentially 2 effects going on here. You've got the single slit pattern and then the multiple slit pattern. And the single slit is the sine beta over beta, or you could call it the sinc function if you want. And the multiple slits is sometimes called the interference function. That's this sine n alpha over sine of alpha. Now, those functions alone would each give you the electric field. If you're interested in intensity, you've got to square them. So I was heading toward a graph of intensity or irradiance, and so I squared them. And then I started sort of drawing crude figures down here, because that's what I do. So I guess I drew them in the other order here for some reason. But this would be the 2-slit pattern, just oscillating back and forth. And it's got peaks at integer multiples of pi. That is when alpha is an integer multiple of pi, alpha being Ka over 2 sine theta. So that's these peaks down here. And the single slit function, sine beta over beta, has 0 when beta is some integer multiple of pi, leaving out 0. So here's beta going down to 0 at pi, and I haven't gone beyond that. But you notice I have scaled these plots differently. So alpha and beta, because we're told that A is 2b, and that gives you effectively the same kind of ratio between alpha and beta. In other words, if A is 2b, then alpha is 2 beta. Or beta is half of alpha, said a different way. So down here, I've got beta being pi, which is half of alpha's 2 pi. So I just scaled them like that. And then I just take the product of these two, and you're going to have these big peaks that kind of shrink under the dotted line that comes from the single slit. But goodness, you can have much more fun with Desmos and actually plot this thing. So I did that. So here's the n equals 3 from Desmos, but of course it's much more fun to do it live. And you can change all the factors and zoom in and out.
You screen share that with us?
Sure. Where did it
Is
go?
Desmos just a like online graphing calculator?
It is. It's exactly that, and it's incredibly easy. I've never used it before, and I've figured out how to use it in about, I don't know, minutes. It's just really easy to use. Okay.
Geogebra is an alternative if you want something else.
You can even do 3D graphs in Geogebra.
What was that?
I said you can even do 3D graphs in Geogebra.
Okay.
Yeah, there's a 2D and 3D graphing calculator in Geogebra.
How do you spell that?
It's like geometry and algebra put together in one word.
Geogebra.
Yeah.
Okay.
Are you seeing it now?
Yeah.
Yep. Okay. So I've got this is 4 slits. So let's back it up to 3 slits. And I've got too many. This is M is way wrong. I can drop this down to 2. And if you want, you can see both functions. It doesn't really help much, but the red is the multiple slit function, and the green is the single slit function. Now I did divide by n squared just to normalize it so it doesn't go off the scale so badly when you have multiple slits. So anyhow, that just makes both graphs go up to 1. Otherwise, the multiple slit one would go up to n squared, which makes it hard to see if you have more than about 2 slits. Anyhow, so the black curve is the result of both. It's the product of both of these functions. Here you can see these split fringes. So there's a large fringe here, a big fringe here. There should be another big fringe here, but it's clobbered by the single slit function and split into 2 halves, kind of. I think it'd be very difficult to see that, but you might, especially if you made n equal to 2. You have a little better chance then. When you only have 2 slits, then these little things might show up.
And how would you actually like look at something like this in the lab? You would run it through both a single and a double slit?
No, you just use a double slit. The single slit function is coming from the width of the 2 slits.
Okay.
It's not 2 different things. It essentially, to get the red curve that's just the double slit function, you would have to have infinitely tiny slits separated by some finite amount. But the slits themselves would have to be infinitesimally wide. As they start having thickness, here, let's show that. No, I can't go further than that. I have to make M. Well, I guess I can change it here. Allow it to get bigger.
And M is the
ratio between the distance, the distance between the slits divided by the width of each slit.
Okay.
And so you can see here now, if I change the scale, let's see, what do I do down here? So here's a case where the single slits are really narrow. They are 1/40th of the separation between the slits.
Okay.
So they're quite narrow compared to their separation. And that yields a black curve here that has a really broad central maximum. So they're getting close to the red curve.
Uh-huh.
But then as you make the individual slits, now this is changing the scale. Yeah, it'd be nice if I could make it work the other way. I could by changing the variables around a bit.
That's okay.
But whatever. If you make the slits themselves rather wide, then you start to see the effect of the individual slits on the pattern.
Mm-hmm.
And that's what's coming into play here. So these are slits that are 1/6 the width, and you can make it worse yet, like so.
Mm-hmm.
So here the slits are separated by twice the distance of their width. I'm trying to think how close, what's possible even. Yeah, I guess if you made them 1, if M was 1, you don't have slits anymore. But the math still gives you something. Isn't that interesting? You literally would not have slits at that point.
It'd just be 2 slits, quote unquote, that are so close or right next to each other, making 1 slit essentially.
Like a double wide slit?
Yeah, and I guess that's what it is. If you look at that black curve, it looks an awful lot like a single slit pattern, doesn't it? So it does work.
Just twice as wide as.
Yeah, just twice as wide. That's cool. Oh my. What if I go to a larger N? It still works.
And N is The number of slits?
Slits. So now
Okay.
this is amazing. This math still works in a case it's not intended for, but yeah, okay. All right, well, so we were supposed to do the one where, what was, M was supposed to be 2, and then you were supposed to look at 2 and 3 slits. So here is the 3 slit, and here's the 2 slit. Yeah, so Aaron, I think you were the one just asked, how would you do this in the lab? You just shine a laser on 2 slits and you get this kind of a pattern, or several slits. You'll get exactly this sort of a pattern.
Okay, so as it goes out to the sides, it'll get dimmer.
Yes, absolutely. Now, this, again, all of this is Fraunhofer diffraction, which means far field.
Okay.
So you've got to be pretty far away to get this result nicely. Or you can equivalently use a lens to do that for you. And that's where in a couple of the problems he talks about if there's a large lens that focuses the pattern. The idea there is that coming out of the slit, you've got parallel rays, and then you use the lens to focus them onto a screen that's not so far away. So then you can get the pattern in a shorter distance inside the laboratory, but you make a smaller pattern that way. It's harder to see in some respects. But that's what I was trying to do in the lab when we had it set up.
Okay.
Let's see, I should stop sharing here and go back to my other camera, I guess. Yeah, what I was trying to do in the lab was get this kind of Fraunhofer diffraction, but just in a short distance. So you can set up a lens to focus things again. Then I was trying to spread out the pattern vertically a little bit. That's where I stuck another lens downstream that was just a cylindrical lens that only spread it in the one direction and didn't do anything with the horizontal direction. That's what I was, just because it tends to be easier to look at when you don't have points of light, but you have sort of a vertical lines. It's much easier to see what's going on. Yeah, and he even talks about there's sort of 2 equivalent. Is that in one of the problems? Where did he do that? That you might think you would need a lens on each side of your diffraction pattern, so that you'd need a lens on the laser side or the upstream side, the source side, to take diverging rays and make them parallel. And then you'd need another lens on the downstream side. It turns out you can get away with just one lens that does both. Here we go, I'll show you.
So, for instance, in number 12, he talks about there being a lens there.
Yeah, that's
And
exactly.
he gives us the focal length of that lens just so we know how far away, like the distance then?
It's telling you the distance to the screen. Yes, that's exactly what that's intended to do. Yeah. And here, let me just here's a picture of a clumsy way to do this. So you've got a source that diverges, and so you put a lens here that turns that into parallel rays, into plane waves, striking your slit system, whatever it is, And then you have another lens here that will take those plane waves, focus them to points on your screen. Well, it's not too hard to guess, do I really need two lenses or can I get by with just one? And the answer is you can do just fine with one, and you can put it on either side. And the focal length that you want for that lens is just as if you were taking this source and focusing it to a point on the screen. And in fact, that's how you set it up. You take the slit out entirely and just get your lens positioned so that you get a real sharp point there. And then you put the diffraction pattern, whatever you've got, right next to the lens on either side. And you'll get just exactly this effect. Yeah, gives you a nice sharp pattern that way. Okay, Aaron, you wanted to talk about the quiz.
Yeah, if that's okay.
No, it's just fine. So I have, like I said, I've looked at it, and here is what I did, which is close to what most of you did. I don't like my notation. I did kind of a crummy job with this. I should change how I labeled the different pieces. But everything's at normal incidence, and so you're calculating the little r reflectivity with n2 minus n1 over n2 plus n1. Transmitted, you could just say 1 minus r if you want, or it's 2n1 divided by n2 plus n1. And at least one of you was a little confused whether I was asking for intensity or electric field. In part one, I'm only asking for electric field. And so the question is only about little r and little t. It doesn't involve squaring it. So the first reflected beam is just, yeah, taking those numbers, and I got 0.1903, I will point out. I think just about all of you dropped down to 2 digits of precision here. And when the first digit is a 1, you really don't have much precision at that point. And when you start subtracting or adding later on, you lose even more. So I'd encourage you to use a few more digits of precision than you are. Yeah, so that's the reflected value. Then the transmitted value, you just use the other formula, and I got about 0.81 is the way you guys would have written it. And then you have to take and figure out what's the reflection off of the back, well, which we call that the interface between oil and water. And just that alone, I calculated. And then that same beam goes through the surface again. And so you've got to go through one more calculation. And you can do those separately and multiply them, or you can put them all into one big calculation. Either way, you all did it differently in that respect. But you end up with 0.047 is the strength, the electric field strength that would be out here. So the two beams have the ratio of intensities is what I've written down here of 0.19 versus 0.047. Then part two, you're trying to figure out what thickness to make this layer so that yellow light is bright. And that's a matter of the optical path length, getting the optical path length. And you want the optical path length to be half a wavelength. And that is because one of these beams is inverted and the other one is not. So this first beam is reflecting off of an increase in index of refraction. So that gets inverted. The second one is reflecting off of a decrease in index of refraction, and that will not be inverted. So these two are already 180 degrees out of phase. And so you want just half a wavelength of additional shift. to bring them into phase, if that makes sense. So that's where I got lambda over 2 as the optical path that I want. You're traversing the thickness twice. I forgot that the first time through the problem. But that's the factor of 2 here. And the optical path length, remember, isn't just the thickness, it's the index of refraction times the thickness. And that factor, I think, Aaron, you may have forgotten. I'm trying to remember.
Yep, I forgot that one.
Yeah. So you end up, the thickness is the wavelength divided by 4 times that index. And that's where I ended up with 98.6 nanometers as the thickness. Then for putting things together, this is where some of you had some difficulties. I think Ebtel actually got it right. It did it a different way. But the bright part is where they are constructively interfering. And the way I got that is just by saying these electric fields add. So I've got the intensity of the electric field, well, right up here, these two electric fields. Those are electric field numbers. So I just add those and then square them and compare that to the case where they subtract and square them.
Does that say 0.0471?
Yeah.
Yes, that's exactly right.
Okay, sorry. It looked like it was saying like 4 pi or something. It was a little hard to read down in part
No.
3.
Oh, in part, yeah, that does look, it's just copying this number up here. I just was scribbling it small. I made so many mistakes in this, it's embarrassing. I was trying to go through this thing, and anyhow. So as I was looking at your answers, I kept discovering what I had done wrong. So I didn't really do, I don't think I would have ended up with any better a grade than any of you, but so what I end up with after squaring these is this 0.056 to 0.021. And then what none of you did, even though I specifically asked in the problem, state the answer as a ratio. Nobody did that. So you're supposed to take 0.056 and divide by 0.021 and get 2.75. I think
I'm pretty sure I did that. I just did it wrong.
Well, yeah, Ben, you had some other mistakes about which was electric field and which was intensity. Ebtel had the right answer. She did it a very different way. So you were using the formula for putting intensities together, as if you have just intensities, and then it's this, what is it, I1 squared plus I2 squared plus 2 I1, square root of I1 I2. And then do you take the square root of that whole thing? I don't remember. Anyhow, well, that, yeah, you do. You have to take the square root of the whole thing. That's a harder way to do it, but it gets you to the same place. You had a factor of 2 in there I didn't quite understand. I'd have to look at that again and see.
I divided by 2 to get like the average of the intensity.
Ah, yes. Okay. Okay, that makes sense. It didn't matter when you're calculating a ratio, you come out with the same thing. Once again, the only difference I would say is your numbers looked like they were very much the same, and you would have gotten the same ratio, except once again, you had like 2 digits of precision, barely that. And so it was a little hard to know for sure, but yeah. So that's what that quiz was. Does that take you through it sufficiently, Aaron, or did you want to see?
Nope, that answers all my questions.
That answers your questions. Okay. All right. Well, you all are still doing just fine. Don't be troubled. I'm very happy with how this course is going. So tomorrow I'm going to do some more presentation on some of this stuff, and I'll have a few more problems for you to do. I was trying to think, there's one problem that you could already look at if you wanted to. If you're just feeling like you don't have anything to do tonight. There was one of these that you can do right now. Oh, I guess I've made two of them now. Okay, let's try 72 and 73 are two that have to do with a circular aperture. And so you could look at those two. We won't look at them tomorrow at all. But if you want to get a head start on the problems, tomorrow I'll give you a more complete list that will include problems that have to do with the other sections that we're going through. I haven't quite figured out exactly which ones we're going to do yet. But so you can start on those, 72 and 73. All right. I think that's all we need to work on today. Did you have other concerns or thoughts? Let's see, we're gathering at 10 o'clock, I believe, tomorrow morning. Then, if nobody has anything else, I think we're all done for today.
John, are you gonna upload the pictures on Moodle, the solution for this assignment?
Oh, solutions, sure, I can do that.
Thank you.
It'll take me a moment. As always, the problem is I don't have a good scanner here. I have to do that at home, but I'll try to remember to do that.
I can text you about it too.
Yeah, you can do that. That's a good idea. Text me this evening sometime, and then I'll make.
I've heard iPhone cameras have a pretty good way to make pictures into PDF.
Well, I can
Yeah.
do that. I just get annoyed. I could just do that here. I mean, I can do it with my Android. It isn't a problem. I've done that before, and turned them into PDFs. I just get annoyed that oh shucks, you know, it flipped it sideways, or getting the light all nice and even and getting it square is sometimes a bother. And so I just wish I had a nice scanner to press a button and get me the perfect result. Of course, they aren't always perfect either, but I find they do better. But yeah. Okay, we'll see you tomorrow at 10, I guess. Bye-bye.
Bye, John.